Shotgun parsers, or how you can parse dangerous data better.
Each of these is for one of you, and Dan gets to fill it for.
Hello. So, having figured out the laptop connection and all that, I'm Sergey Bratus. It's my great pleasure to introduce Meredith Patterson, who was the co-creator of the LangSec, Language Theoretic Security field of research, and TQ, who joined us in that field. And we're going to talk today about what we call shotgun parsers, and that's obviously not a good thing. And about how to avoid them. So think of this pattern as an annotated parse tree of an annotated basic block tree of your code. Some of those dots are checks of conditions that hopefully prevent your program from being exploited. Some of those are your processing logic, and they're all interspersed. And the name for this is a pwnage, because the unchecked processing logic that makes assumptions that are simply not true tends to compose into the exploitation.
We're going to refer to design patterns a lot over the course of this talk. And I just want to make clear that the shotgun parser pattern that we are referring to is emphatically an anti-pattern. Patterns that you should not be engaging in. Patterns that if you see, you should ferret out and destroy at your earliest convenience.
So the way we're going to do this is we're going to travel to the past, just like the beagle, and collect specimens of famous bugs and show that, in fact, those bugs were caused by a shotgun approach to parsing. And besides just collecting those wonderful finches, we're going to try to build a classification of vulnerabilities that come from bad parsing with a view of constructing a better way of parsing the data that you should really be afraid of, that you really don't trust, that comes from an untrusted source or can be manipulated on the way. Now, the important thing about this is that for now, we're not making claims about how fast it can be. We're talking about secure and possibly slow, but hardened stack. And again, we do not claim to know how to do that in full scientific glory, but we're really constructing something of a cladistics of the parsing mistakes, of the parsing errors, and we are going to present a few of them, and hopefully the voyages will continue. So these are dispatches from the LangSec ship Beagle. The examples that we're going to take are quite complex software. And this is not just any garden variety software. It's a software that people depended upon and still depend quite a bit. And even if in those complex cases things went wrong, we must understand what it was that went wrong and see where the problem crept in. And in each of those cases, we see that a mistake was sort of inevitable because the underlying data format was actually hard to parse. It required much context in order to parse it. And at some point, that context was lost, and an assumption was taken, and that led to pwnage.
So, just to recap everything that Sergey and I have been talking about for roughly the last 2 years now, we strongly advocate full recognition of input before processing. This sounds simple. it's easy to fall off the wagon, but basically speaking, you have a recognizer which handles your input as a language. It treats the input as a language. If that input language is context-free, such as JSON or YAML, then it is parsed with the proper context-free grammar for that language. If it's something context-sensitive, such as HTTP or DNS, then again a suitable parsing automaton is used. Once recognition is complete, either the input is accepted or rejected, then expectations can be enforced on the subsequent code via design by contract. Then, and only then, once once all of your assertions have passed, I mean, this is 00101, then you can safely process. And I've gone and forgotten to talk about all the different finches again, because I'm a terrible person. I'm sorry, Sergey.
Well, so the lesson from the finches here is that
they eat different things. They consume different protocols. They need to be different, logically well-separated components simply to make your engineering life easier. Because if you've somehow managed to intermingle different layers of a stack in a single piece of code, then you've introduced context that that you didn't need, and you've only made your own life harder. This is why separation of concerns is a phrase.
And this is what you will get if, well, again, let's do the finches again. So for every kind of food, you have a special kind of a beak. They specialize. If the beak would be used on the wrong food, you will clog the intestines and your finch will go belly up, or whatever finches do. So you have to sort of bring the right beak to the food, or the right weapon to the fight. It does not do to parse something that is context-free with a finite state machine. We will see an example of that. In fact, the recent Rails bugs were the example of that. There is a wonderful bug that happened in 2010 and got the pony for the most epic fail, and that was the anti-XSS Internet Explorer measure. In applying a finite state machine to rewriting HTML, which is actually worse than context-free, they actually got pages that were not vulnerable to XSS to be vulnerable to XSS. So the principle that we're advocating is that you have to bring the right recognizer that matches the input that you're consuming, or else it's bad news for your finch. And by the way, the tool using finch is real. There is really such a thing. I mean, the next stage would probably be weapon holding finch or weapon designing finch. But in fact, we'll keep you in suspense until the last slide. Then we'll show you the finch that probably tops the tool using finch. Anyhow, so we've seen this before. We've seen this over and over. The way, this is the Lulz boat, which has come for so many sites and so many designers in the course of the past few years. And the reason why it came and made itself at home was that input, this thing called input sanitization. So you have this myth that's ingrained in terminology that there is bad stuff in input, but that's okay. You can suppress it. You can sanitize it. And this is entirely wrong. This is the root of all lulls. This is the root of all pwnage that has been happening to PHP, for example. Because people are trying to suppress bad stuff based on some kind of ideas of bad stuff. Oh, we'll throw in an extra magic quote. Wonderful. Now you've created a vulnerability where none existed before. The point is that it's not about sanitization, it's about recognition. What makes your message valid is that it's a phrase in a formal language And an automaton should be brought to bear to recognize it. You have to have the right beak. You have to have the right front end. You have to have the right recognizer. And your correctness of your input.
As the recent XKCD pointed out, I had 99 problems, then I used regular expressions, now I have 100 problems.
So another variant of the same myth is that, oh, you can do escaping. Again, think about this. Your correctness assumptions are in fact assumptions of a language. Of a formal language, there is an automaton that should be able to recognize that formal language. If you treat escaping as just strings replacement, well, there are people who will take your code and build a weird machine out of it because, you know, escaping is also computation. Escaping is also a kind of an automaton, and they will find their way to construct one such.
Actually, I think the logo is a tentacle wrapping around the Ruby. I just realized that. It's got a facet on it. That's awesome.
Yeah, so that's Ruby on Rails.
All right, so where it gets even worse than this is the idea that you can just suppress bad things in both your input and your output, and that'll be just fine. So the problem here is that if you try to, so the Python user guide, believe it or not, has a great phrase for this. It's called changing horses midstream. So you know, they use this phrase in the part of the user guide where they talk about operations on a list that work in place. Delete being an example, and they warn you, in the beginner's guide, don't ever delete things out of a list that you're iterating over, because you're going to end up in some sort of nasty runtime situation where you run off the end, and that's never supposed to happen in a language that manages memory for you, right? Well, but if you're doing that sort of thing in place, that's the problem. And similarly, if you're trying to, at the same time, mung your input and your output, you're going to introduce weird machines.
So XSS has been a source of those because, yeah, you're protecting, you're reading in the page source, and then you're trying to modify that so that the user is somehow made aware of the XSS, or you somehow break the XSS. And this just is such a source of the halting problem. It's just can be done. So we promised you finches, but in fact, let's start with a pony. IE8 deployed this system for breaking standard idioms used in XSS. So they would take an object or a link or an iframe and insert an extra character. If the idiom looked like it was indeed evil XSS. And what they did was they took a regexp, and you can actually see examples of some of those regexps, and then they applied them to server responses. And the problem was that you could actually craft the input in such a way that being non-vulnerable to XSS, it became vulnerable. And this is the paper that actually has a demo online, and it's just awesome. And then Google, of course, saved the day by introducing this new header, XSS protection 0, meaning, please, please don't protect me. Yeah, that's really the reaction that you should experience when you're seeing a regexp being applied to that fight. It's a much richer language, class language. You can just not handle it with finite state machines. So substitution, such as what the regexp does, is actually computation. If you find a component that will do it repeatedly for you, you can actually get up to the Turing machine power of a computation. So watch Mario Heinrich. his Got Your Nose talk or his paper called Stealing the Cake Without Touching the Sill actually showed that using the password manager that would continually provide, try a password, try to fill it in into the web form. And he managed to use that for a loop. He managed to use the SVG elements rendered conditionally for bringing the if, and suddenly you had quite complex computations in your browser. But, you know, things get better.
So everybody is probably well familiar with the Ruby on Rails, or the spat of Ruby on Rails vulnerabilities that's been coming out over the last couple weeks and / or months. In particular, CVE 2013-0333, which is the YAML the JSON parsing bug that was really a YAML parsing bug. So to quote the best description of it the description of the proof of concept for this bug. Basically, they had the problem that they needed to parse JSON, and they had this perfectly good YAML problem. So they used the mathematician solution, which is to reduce the problem of parsing JSON to the problem of parsing YAML. And they did so by running a bunch of regexes on it, and they looked at the parts of the JSON syntax that were not in YAML and changed them to the equivalent YAML forms, but didn't think about the bits of YAML that weren't in JSON. And so sorry, I haven't spent too much time looking at these slides. But the thing is that they could have just used a JSON parser. These things exist for Ruby. And they parse exactly the syntax that is JSON. And there would have been no bug. But instead they had to, they bolted on top of the Rails, so the Ruby serialization to YAML and had a problem. In particular, there's this particular, YAML has this particular syntax feature of having tags, which are in Ruby treated as functions to call to process or to convert a data structure into some Ruby object.
So what they were actually doing here was they were not parsing JSON and transforming it into YAML. What they were parsing was some bizarre hybrid of JSON and YAML, because this dash 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 and the hash, the hell's that thing called again? I don't sodding speak Ruby. But yeah, no, I mean all that business at the beginning is not actually valid JSON. It is valid YAML, and the convert JSON to YAML method simply allows it to be parsed as YAML, which makes no sense. You're not supposed to be parsing YAML, you're supposed to be parsing JSON. But because you're able to simply leverage YAML straight into this method, you're able to use that to represent any sort of object that Ruby lets you represent in YAML, which is to say anything.
So now, hopefully we've convinced you that the mismatch between the language of the data format and the language that your actual parser is capable of checking, capable of recognizing, is a bad thing. And with the Rails bug, I mean, we can describe it in just one word. Instead of recognition, they did rewriting and then not exactly recognition. And then parsing that somehow assumed that in the process of rewriting, the code was, the input was already checked. That's really the worst way to go about it. But, you know, from those, and basically that's when your Finch is dead. You apply the wrong sort of processing, and it's got us clogged, and there you go. But in fact, let's look at very, very angry Finches, at extremely impactful bugs that seem to do the right thing. And now we're talking C, right? It's a little bit puzzling how people manage to shoot themselves on the foot with managed languages, but here is a C that makes mallocing while you are parsing such a damn big deal, because you are allocating memory and you're copying bytes, and you can construct, that's already enough for construction of an exploit. So the three examples are going to be OpenSSH pre-auth challenge response, a bug that gave remote code execution, pre-auth. This was done by Goebbels in 2002. Bind, of course, was the mother of all problems for quite a while, so it's an older bug, it's 1999, and that's the next record buffer overflow. And again, we're going to talk about how that happened and how it should not have happened. We're going to present a tool, a parser constructor, that allows you to bypass those two, avoid those kind of subtle bugs.
In C.
In C. So, and finally, we're going to look at the famous OpenBSD remote IPv6, ICMPv6 MBUF overflow, which again gave remote code execution on BSD boxes. And that was in 2007. And then again, we'll talk about why and how to avoid this. So you treat your data format as a language, and the thing about it is that if your assumptions made by the code about your C data structures are connected to what makes a proper phrase in this language, well, treat it as such. Apply recognition. And if you have context sensitivity, if you have multiple fields that must agree in value for your input to be correct, never forget to check that.
More to the point, if you describe your inputs formally, it becomes easier to validate those relationships between elements, because when you're no longer thinking about, oh God, I have to make sure that this value and the length of the thing that this pointer is pointing to are the same, and I have to check all these other things in all these other places, you can describe these validation relationships in a much more structured and principled way that actually expresses the relationships between, you know, for instance, you know, a parser and a sub-parser, which we'll actually see an example of in just a moment here. But basically, you know, the overall idea here is just to make the code that you're writing look a lot more like the spec that you have written down, even if it's just in your head.
Yeah. So here is this challenge response bug in a sub-parser of that particular phrase of SSH challenge response authentication options. And this is what the code looks like.
And this looks really simple, right? I mean, how could this possibly bite you? Well, let's walk through it. So the very first thing that happens is we pull 4 bytes off of the incoming packet. That's, you know, 32-bit integer. If that number is greater than 0, that looks like a sanity check, right? Fine, wonderful. Then we start, then we start allocating space for a bunch of strings, which are effectively C string. Effectively Pascal-style strings, which is to say a length and then that many bytes. But what happens, anybody, if the nresp value is larger than 2 to the 30th? Exactly. Yeah, so that overflows. So let me just walk you through the entire exploit really quickly. So there's the packet getString that gets called there. I mean, that's normal. So a buffer, yeah, so packet getString calls buffer getString, which starts pulling starts pulling strings off of the packet that was sent. These strings, by the way, are shellcode just putting itself into the area off of the end of the array that you've already run into, because, you know, if you overflow it to where you've just mallocked 4 bytes, cool. Now you're allocating lots of space for strings full of shellcode. So that when you bounce into fatal, because you deliberately put a packet that was too long, so that meant that it choked and said, nope, we're not going to take this. It looks too big. We fall into the execution handler, and because we laid down all that shellcode earlier, we stomped on the function pointer that gets called on the context of the packet, and the pointer gets dereferenced and you win. That's where that's how you end up getting your shellcode called. So how do we do this right? So this is one of the 2 idioms, essentially, for expressing a parser in Hammer. And so how would we express this, an int followed by that many strings that are specified by length and value? Well, first we read an unsigned int, 32 bits. Then we read, then we start reading, I'm sorry, that should have been h many, h length value. I'm terribly sorry for that typo, guys. See, I'm sorry, no, I wrote that wrong.
Basically, what is going on is that you have, or you read an int, and then you read that many strings, each consisting of an int and then that many bytes.
Thank you, dear. Yeah, my indentation screwed me up. I totally boffed that one, sorry. Anyway, point being, when you see what looks like a special case, check your premises and figure out which one is about to bite you in the ass. Because either your input data language has some quirks, in which case that's okay, just, you know, define that formally, or you're digging around into and out of your syntax semantics boundary, which is what happened here. You were using an unchecked result, which was semantically derived, right? You got this value you extracted this value out of your syntax. Now it's semantics. Then you apply an operator to it. It overflows. You still didn't check it, and so that's why your logic is bad. That's your premise where you screwed it up.
So you could put it differently, right? Again, look at this code. It starts allocating memory and copying bytes. That's what packet getString does. While the packet is not yet traversed. This function would error out if the packet is not entirely consumed and the length value options are not taking up all the packet, but it's too late.
Because we never actually get there, because because a string that claims to be too long for the implementation causes the call to fatal, and so that's how we get out of that loop.
And so the recognition is never completed. In fact, your recognizer is hijacked, such as you have it. Your parser is hijacked from under you. Instead, you should be writing it like this, specifying exactly what is it that you expect, what is followed by what, and exactly where the packet needs to end, right? This is the parser. This is also the spec. This is the way to do it. And Hammer, the parser construction kit that Meredith and TQ are working on, lets you do this, specification-based parsing, with what is essentially parser combinators, but we're not going to say that, in C.
No, I will go ahead and say it. I mean, it's a way of writing inline domain-specific languages in C.
So let's, and that would have saved that particular subparser from being exploited. Let's look at another bug, which is bind 8.2. When bind introduced this a special kind of a record called NXT to say to the requesting client that, you know what, there is no name like this. But how do you represent a negative? Well, the way you do this is you're saying, okay, between this name and that name, there are no names. So that gave you basically, the response gave you basically a pair of names saying that, no, that range is unpopulated, be warned. And this has gone through a couple of updates. The way that exploited servers via a bug in the target name server, the target parsed the NXT record and got owned, was actually quite interesting in that the target was the name server and an exploited name server redirected to another one which in a recursive lookup which delivered the payload to the target, and the target dropped the shell. And we found that code. It turned out to be sort of buried in various repositories, but we'll have an annotated version of it online. And this was the ADM crew that exploited that. So in order to see how that went wrong, we should understand the DNS format first. The thing about the DNS format is that it consists of these RRs, resource records, which follow the header. And those RRs do what they call compression of domain names. And the compression is really just back-referencing of the previously occurring strings in the packets. So if you need to replicate a bunch of names, you don't, in fact, replicate them. You instead say, OK, look this far back into the packet. And you will find that string ending with for this span. And so what this means from the point of view of parsing RRs is that you have to keep track of every RR and every name just to know how long your names are. This is very context sensitive. And this is, of course, every time you see a length field in the data format of, and here is your typical RR, and here is your R data here's your data that was described by this length with the next domain name in the NXT record. But every time you see a length field, you should be worried, especially if those length fields have to agree with each other over the span of the packet that you're parsing. So when you have a shotgun parser, Mr. Length field is no longer your friend. So the domain name is compressed. It can only be checked after all the names have been expanded, so you need to keep all that context. And so you see code like this.
All right. So it starts out with the compressed domain name being expanded. That's in line 2. Where things actually start to go wrong is down in line 13, where you see that we've got well, 12 and 13. So we increment the position of the current character pointer CP where the compressed data starts by the length of the expanded domain name, which is kind of odd. Why don't you continue with that?
Yes. Remember, you have all of those RRs, your previous packet, and the lengths sum up. So in order to have enough of a buffer and to do memory copies of those names properly, you start depending on the lengths in RR records.
Honestly, I'm of the opinion at this point that if you're dealing with offsets like this, that's actually a code smell. I mean, like everybody knows, the 2 hard problems in computer science are cache invalidation, distributed naming, and off-by-1 errors. So,
yeah, and you look back. So basically, you look back in the packet, right? And you derive the string length of what you had back there, and then you copy memory, and this is where the crafted strings in the previous RRs bite you and you overflow the buffer.
Why should anyone have to be doing arithmetic in order to parse things?
Yeah, we should probably put this on another one of those slogans.
So, as Sergey said, if you're having to keep track of the semantics of, of things like length fields across an entire span of data are just not safe. You run into similar kinds of allocation errors as what we ran into before. So now I want to talk about how we do this in Hammer with the other API that was actually just recently pulled in thanks to a pull request sent by Sven Halberg, the greatest user ever. So you'll notice that the syntax looks a little bit different here. We've got a parser called the init character string. But what's that doing here? Actually, that's a function that returns that returns a parser, and that top one is static. I'll buy a beer for anybody who can tell me what that design pattern's called. Really? No. Yes! Thank you. Okay. Bear in mind, like, I don't actually do security for a living these days. I work in engineering. I'm slogging in the trenches, just working with people that sling C and Java day to day. So maybe my expectations have changed a little bit, but yes, that's called a singleton. And the reason why we're using this is because, and this is actually in the repo right now. If you go to github.com, oh my God, we're totally out of time. Shit. All right, well, I'll go through this quickly then. So we create a singleton. Now we've got, you'll notice these macros here, HA rule. So we've got a family of macros that Pesco came up with for constructing rules with validation, rules by themselves, rules with actions attached to them, and rules with everything. So here what we're doing is we make sure that that singleton exists, and we're attaching a rule to it that I'm not actually going to show you, because what I am going to show you is the rule that the macro is going to expect to apply to this text record and process it. And this is all it is. I mean, this is just about the same length as the previous code. It's the backend API for extracting stuff out of parsers is a little messy, but I'm more than happy to introduce everybody to it later, and we're working on docs.
But notice what it doesn't have. It doesn't have arithmetic. It doesn't have mallocs that take the arithmetic that you do on the input data.
You do see some mallocs there, but what you're seeing there are actually mallocs off of an arena allocator, which TQ wrote me for my birthday last year, so that we could make this thread safe and reentrant.
The important thing about such mallocs is that you can discard them safely without having them hijack your parser. So we are running low on time, so we're going to rush through the OpenBSD kernel mbuff overflow, which was completely amazing. I maintain that this is one of the absolutely stellar bugs, and as angry finches go, this is the one that really, really bites you.
Just show him, dude.
Yes. It was found by Core Security, by Ortega and Guerra, who presented that in April 2007. And there was a Black Hat talk on it and a DEF CON talk. And it's just, it exploits the fact that the IPv6 as a protocol is a chain of these extension headers, which can vary in size, and it's just strewn with length fields. The length field or the next header field that identifies the next header and the next header and the next header. The funny thing is that you can mix and match those headers, especially when doing fragmentation, in interesting ways. So this is your typical IPv6 packet header, and this upper layer header, this next header, which eventually goes to your TCP or UDP, locates the next header in the record, and then the next one, and then the next one. So you have this chain. And this chain is mapped into OpenBSD's packet fragment allocation. The packet fragments are stored in structures called mbuffs. Those mbuffs are chunks of the packet, and you can have a chunk of the packet that either stores the packet or sends off to another buffer. Interestingly enough, it can also contain a function pointer to what you need to the function that you need to call to clean off, to clean up the packet from a buffer. That pointer gets overwritten. But what happens there is that you have two chain structures, right? Two chain languages. And they are stored in this chain of mbuffs. When the languages do not align, when the offsets do not align, things get really interesting in that you can overflow the mbuffs by mixing the right set of fragments in the input. It's very context sensitive, and it was not handled right. So this was the function where the problem occurred. It's called mpulldown. What that function does is it... Yep.
What I'm saying is we don't have time to step into this.
Yes. Yeah, we don't... so again, what this function does is it reallocates the fragments of the packet across several fragments when you need to get one span of it for actual parsing. So it continually changes the chunks from under the packet. It's and you know, this is the story. But the reason why the story is there
is, oh my God, 451 lines omitted in that function? This is a code smell. This has a name. This has a name on antipatterns.org, and its name is Taller Than Me. So bear in mind, you know, a code smell does not absolutely guarantee that something is wrong in your code, but 9 times out of 10, when you see something that just looks freaking funny, that's going to be a sign that, you know, look deeper. Because when you have just too much stuff going on in one function, sometimes you are violating separation of concerns. You know, a function should do one thing and should do it well. What they were trying to do was to keep all of the operations in a method at the same level of abstraction. They're assuming one layer of the network stack is a layer of abstraction, but syntax and semantics are different layers. Sometimes pieces of parsers are different layers. You know, it all depends on what languages you're using, what protocols you're using, and how they compose together. I'm going to skip this stuff about offsets because we really don't have time. But I just want to point out another anti-pattern here. So you notice how, like, the way that they fixed this bug actually just increases the indentation here. It's just more freaking special cases. Thanks, guys. This is another anti-pattern. When you're saying, you know, if all these things, you are setting yourself up for a special case that you didn't catch. And there it is right there in the code. But here's where things get a little messy. We have one more Finch to introduce you to.
Well.
So, story time. And we'll keep it a short story because we're right about out of time. But first we'll step back a couple years to 1972.
I wasn't born.
Neither was I. The internet was not really that much of a thing back then. So there was an operating system called 10X that was descended, it was the unofficial operating, it was one of the unofficial operating systems for the PDP-10. Built on top of TOPS 10, the context of it is fairly unimportant. The important bit is that there was the way that you checked passwords on it to do authentication is you called a kernel function that looked vaguely like this. Originally it was written in PDP-10 assembly, and it did PDP-10 assembly like things like passing around length fields as part of the pointer. So this is idiomatically translated to C. So obviously, there's a vulnerability here where you could just pass in a password that's not null terminated. You can stomp over, or you can walk on arbitrary, or you can touch arbitrary memory. However, there is also an exploit that is much more subtle that comes from what happens if you put the password that you pass in just off of a page boundary, where the second page, where the rest of the password is either on slow disk or even slower tape, or not even there at all. So what happens is it checks the first character. It's like, oh, that's valid, and goes on to the second character and causes a cache miss, which takes an enormous amount of time. Or if the first character is invalid, it returns immediately. And so you've got a nice timing oracle to reduce your password cracking attempts to roughly milliseconds.
So, I mean, the scary thing here, and this is why this guy's the vampire finch, is because, you know, Hammer's not going to save you here. You know, it's not operating at the level of, you know, at the level of page boundaries, apart from, you know, what we did with the arena allocator.
Right. Oh, it's worth mentioning that there's a weird machine there. And unlike most of the weird machines that we've been looking at, this is not a very complex weird machine. This is a regular weird machine.
But the point is that it's still functionality that emerged from two systems being composed together, which is to say the page fault handler and the password and the password routine. They composed together into a state machine that did not exist before.
And this is really what you want to avoid when you're dealing with your parsing. You don't want to expose arithmetic and memory allocation and copying before you are sure what it is that you're allocating and copying. And essentially, your parser should derive from the specification. Or in case of Hammer, Hammer allows you to actually write the parser as a specification. Then you should avoid doing any arithmetic in the recognizer. The recognizer is not a good place for it. You should avoid complex systems of offsets and complex alignments of one structure that's chained over another structure that's chained. And that's heaps. That's why you need special protected arenas for parsing, which again, Hammer gives you. And then, of course, you know, here's the vampire finch. There is blood in its beak. You're still not quite safe. There are still timing attacks and architecture that will get you, but at least it won't be from a memory corruption. So the takeaway.
As we've been saying all along, please, what you are saying, what your users are saying to your application, what other people's machines are saying to your machine, you know, these are all languages. Please treat them that way. Please try not to use context-sensitive data formats if you can get away with it, because we've just seen some pretty gruesome examples of just how much root shell doing that can get you. You know, but at the same time, also, if you're going to be operating on a context-free language, operate on it as a context-free language, not a regular language. We've been taught, you know, I've been bringing in design patterns into this discussion because I think this is a conversation that we really need to be having with engineers who are not necessarily security people, because that's their language, that's their idiom, that's what they know how to speak. You know, and we can also talk about data patterns. We're talking about establishing data languages, specifying them in line, and, you know, just using them as part of your code. It's not a separate thing. You just write them the same damn way you do everything else. But as as a component, it is a separate piece. It takes care of itself, and you make sure that you can compose it neatly with other parts of your code.
Or else other people will compose it for you on your machine. We should open up for questions.
Yeah. Questions? Yes.
Which is cooler, finches or owls?
The owls are not what they seem. Anything else? I see a hand. Okay, in the front row. Yeah, so I like Antler. If you're using Java, go ahead and friggin' use Antler. As I recall, it just had a really nice new rev.
Java or any of the other dozens of languages that Antler supports.
The problem with Java, of course, is that it serializes and then it deserializes. And as the recent spate of O days has shown us, it doesn't quite do it right.
But at the application layer, absolutely. Antler rocks. Totally go with it. Antler's great. I love it. Anybody else? I know. Yes, again. Yeah, no. If you're writing up a specification of a language, BNF is totally the way to go. You know, their RFC 5234 is the RFC definition of the advanced Bacchus-Nor format, which was designed to be able to describe pretty much everything that you might want to be able to cram into a protocol. There are some exceptions. The comment field is a problem. But by and large, RFC 5234 is actually self-describing, which is kind of neat. Like if you implemented a parser for the ABNF in RFC 5234, you could parse all of RFC 5234 with it.
But in reality, you know, you will find yourself writing simple subparsers for things like type length value or length value?
Yeah, well, I mean, like the DNS example that's actually sitting in the Hammer repo right now is I like to think at least a pretty nice example of that because it abstracts common functionality that both resource records and like the rest of DNS use. Resource records are sort of abstracted off into their own little module, and the rest of DNS is too. And we're building towards a standard library, like a reference library of protocol and message format implementations so that nobody has to sodding well do this anymore themselves. And DNS was our first step. So we're working on that.
And I should, again, stress that this is in C. Right? You can get nifty academic parser generators. We'll be happy to provide you a bibliography in Haskell and other Scala and other languages. But you really are down to, when you're parsing packets, you're really down to parsing C.
And the other thing that we did with Hammer that I keep forgetting to bring up that actually no other parser generator library out there does is Hammer is bit-oriented. Yes, you can comfortably and conveniently parse single-bit flags, out of byte-oriented data, and it doesn't hurt. So we should do it like that. Use Hammer.
The other thing that is worth bringing up about Hammer is that it supports, well, kind of at this point, but it will support soon, multiple backends. So all of those neat tricks that Rob Graham talked about in his talk this morning, to handle 10 million connections at once, yep, we do that.
It's all just a language. Rob speaks it too. Anything else? Yes? Yes, we actually do. That was such a pain in the dick, but it works. Yes. So Dan Kaminsky actually challenged me, write an ASN1 parser in Hammer blind, like don't test it against anything, and throw it against the Protoss test set. That's in the queue. I'll be doing that soon and like just publishing results, and that one's going in the standard library. I'm sorry, I did Burr in Haskell, that sucked. Somebody else? I thought I saw another hand. Yo.
Well, so due to the nature of how IPv6 is designed, it is difficult to write a good parser for it. And for future protocols that are designed, we should keep that in mind. This is not a reason to not use IPv6 This is just a reason to look a little bit closer at the parsers and give them a bit of extra testing.
Well,
Because, yes, they probably screwed it up at some level.
It's hard not to.
We'll put the commented code from those vulnerabilities online and show exactly where they got carried away with passing semantic information as an offset into a packet. So the fact that a particular chunk was aligned at the head of the mbuff storing the packet was actually meaningful for that function. And that semantic queue was misinterpreted, and that led to heap corruption. I mean, I would refer to the mbuff as to the mbuff storage as a very customized, packet-oriented heap. But obviously, that problem exists, and it is going to bite us in the ass. It is going to be continuing. Well, again, you know, Vampire Finch. Actually, I mean, that's blood on that beak, right? I thought that the tool using Finch actually topped it. But yeah, that problem will recur. If you're interested in looking at IPv6 stacks from this point of view, we might give you some pointers where we think it's really bad.
Any more questions?
All right, thank you all.